equipped with 5 senses. Man explores the universe around it and calls the adventure science. These were the words from a boy, born in November 1889 in Marshfield, Missouri. He is often regarded as one of the greatest astronomers in history. With a rich educational background, including a degree in mathematics and astronomy from the University of Chicago and a Rhodes Scholarship to Oxford, he bridged the realms of science and philosophy. His groundbreaking observations of galaxies in the 1920s revealed that the universe is expanding, laying the foundation for the Big Bang Theory. His work revolutionized our understanding of the cosmos, forever changing humanity's perception of its place in the universe. He is none other than Edwin Hubble. The universe, vast and enigmatic, stretches beyond human comprehension. It is a theatre of extremes, where the drama of existence plays out on scales that defy imagination. From the infinitesimal quantum fluctuations to the sprawling cosmic web, each phenomenon underscores the fragile balance of reality. We are fleeting observers in an orchestra of chaos, light, and shadow. Yet, our curiosity propels us to probe the unfathomable, to seek meaning amid the void. Every corner of the cosmos is a testament to the profound interplay between creation and destruction. Stars are born in the violent collapse of interstellar clouds, only to end their lives in fiery supernovae or quiet fades into darkness. Galaxies collide, merge, and reshape, leaving trails of havoc and new beginnings. Even in the apparent stillness of the vacuum, quantum fields dance and fluctuate, hinting at the latent energy that underpins existence. The universe, it seems, is in constant motion, a dynamic system of balance and imbalance, order and entropy. This cosmic ballet evokes a deep sense of wonder and humility. It challenges us to confront our insignificance in the grand scheme of things, yet also inspires awe at the intricate mechanisms that govern everything from the smallest particle to the largest galaxy cluster. To ponder the universe is to reflect on the dualities of existence, permanence and impermanence, chaos and harmony, light and shadow. It is a reminder of the beauty that can arise from chaos and the destruction that often precedes renewal. As we gaze into the depths of the cosmos, we are met with more questions than answers. What lies beyond the observable universe? What is the true nature of time, space, and energy? Are we alone in this vast expanse? Or are there other sentient beings contemplating the same mysteries? These questions are as old as humanity itself, yet the answers remain tantalizingly out of reach. In our quest to understand, we build tools, craft theories, and embark on journeys of discovery, driven by an insatiable curiosity that defines our species. Through this lens, let us delve into 5 astonishing phenomena that challenge our understanding and ignite our wonder. Each reveals a unique facet of the cosmos' grandeur, offering insights into the forces that shape our reality. These phenomena, both terrifying and spectacular, serve as reminders of the universe's immense power and the delicate balance that sustains existence. You're watching Space 9, unveiling the mysteries of the cosmos, your gateway to the universe. Massive water reservoir, discovered in a groundbreaking discovery that has sent shockwaves through the world of astronomy. Scientists have detected an enormous water reservoir orbiting a distant quasar, located a staggering 12 billion light-years from Earth. The size of this discovery is beyond imagination. The water in this reservoir is estimated to be 140 trillion times the volume of all the Earth's oceans combined, an amount so vast that it challenges our understanding of the cosmos and its capacity to harbour such enormous quantities of water. This discovery not only raises profound questions about the nature of distant cosmic phenomena, but also opens new avenues for understanding the distribution of water and its potential role in the formation of galaxies, stars, and even life itself. To fully appreciate the significance of this find, it's important to explore the details surrounding the discovery, the science behind it, and the implications it holds for our broader understanding of the universe. The discovery was made by a team of astronomers using one of the most powerful observatories available, radio telescopes. The water reservoir was detected around a quasar, which is an extremely bright and energetic center of a distant galaxy, powered by a supermassive black hole. Quasars are some of the most energetic and luminous objects in the universe, often emitting more light and radiation than the rest of their host galaxy combined. The quasar in question, located 12 billion light-years away, provides a window into the universe's past. We are observing it as it was when the universe was in its infancy, only about 1.5 billion years after the Big Bang. This time frame is crucial because it provides insight into the early conditions of the universe and the processes that occurred long before stars, planets, and galaxies took on their present forms. The water was detected in the form of a molecular cloud, a vast region of gas and dust, which is typically where stars and planetary systems form. These clouds are often composed of hydrogen and helium, the most abundant elements in the universe. But this particular cloud contained a surprising amount of water vapor, enough to account for 140 trillion times the volume of Earth's oceans. This water vapor, which is in the form of hydroxyl molecules, OH, was detected through its absorption of specific wavelengths of radio waves emitted by the quasar. By studying these absorption lines, astronomers were able to estimate the amount of water present in the cloud with remarkable precision. To put the size of this water reservoir into perspective, let's compare it to the total volume of water on Earth. Our planet is home to approximately 1.332 billion cubic kilometers of water, with about 97.5% of that being salt water in the oceans. The remaining 2.5% is fresh water, much of which is locked away in glaciers, ice caps, or underground aquifers. The water found around the quasar is 140 trillion times the volume of all the Earth's oceans, a number so large that it is difficult to truly comprehend. This discovery raises several important questions about the distribution of water in the universe. The vast quantities of water found in such a distant and ancient cosmic region suggest that water, in some form, may be far more common across the universe than previously thought. Water is essential for life as we know it, and this finding may indicate that the building blocks for life could be more widespread in the universe than we had realized. If large reservoirs of water can exist in the farthest reaches of the universe, then the possibility of life existing elsewhere, on distant exoplanets or moons, becomes more plausible. Quasars are not just incredibly bright, they are also incredibly important in the context of galactic evolution. They are powered by supermassive black holes at the centers of galaxies. These black holes are surrounded by massive accretion disks of gas and dust that spiral inward, emitting vast amounts of radiation as they are consumed by the black hole. This process generates the intense brightness that makes quasars visible even at enormous distances. The discovery of water around a quasar offers a unique glimpse into the processes occurring in these early, distant regions of space. When galaxies form, they go through various stages of development. The central black hole in a galaxy's core grows as it accretes material, and the surrounding gas cloud can become a site of intense star formation. The presence of water in these distant regions may suggest that conditions for star and planet formation are already in place in the early universe. It could be that water, one of the most fundamental substances for life, is a byproduct of the processes that allow galaxies to evolve, providing a crucial component for the formation of habitable planets. Quasars are thought to play a pivotal role in shaping their host galaxies. The energy they emit can influence the surrounding environment, either facilitating or inhibiting the formation of new stars and planetary systems. The presence of vast amounts of water vapor near a quasar suggests that, despite the intense radiation from the supermassive black hole, there are still processes occurring that allow for the formation of molecules that are critical to life. This finding challenges some of our previous assumptions about the relationship between quasars and the environments surrounding them, particularly in terms of their ability to support the molecules necessary for life. The discovery of such an immense water reservoir in space brings us to a broader question. How common is water in the universe? Water has already been found in various places across the cosmos, from distant nebulae to the icy moons of our own solar system. Observations of comets, asteroids, and the outer planets have all revealed the presence of water in different forms. It is believed that water was likely abundant in the early universe, possibly forming soon after the Big Bang, when atoms and molecules began to coalesce. The discovery of water around such a distant quasar suggests that large quantities of water may be present in many other distant and ancient regions of space, particularly in molecular clouds. These clouds are often considered to be the nurseries of new stars and planets, and the presence of water could be an indicator that conditions conducive to star formation and potentially the formation of life are widespread in the universe. In fact, water may not be a rare commodity in the universe at all. As astronomical techniques improve, scientists are likely to discover even more water reservoirs, perhaps in unexpected places. From the ancient cosmos to modern star-forming regions, the presence of water could be more common than previously imagined. This raises the exciting possibility that water, and by extension, the conditions necessary for life, may exist far beyond the confines of our solar system. The discovery of such a massive water reservoir raises important implications for the ongoing search for extraterrestrial life. Water is considered one of the key ingredients for life as we know it. The presence of water vapor in a distant quasar's molecular cloud implies that the basic components needed for life may be more widespread throughout the universe than scientists had originally thought. This discovery lends weight to the idea that, in regions where water exists, the potential for life, whether microbial or complex, could also exist. The question of whether life exists elsewhere in the universe has been one of the driving forces behind astronomical research in recent decades. Missions like the search for exoplanets in the habitable zone of distant stars, the study of Europa's icy surface, and the exploration of Mars are all part of this broader quest. The discovery of a massive water reservoir so far from Earth is a reminder that life does not need to occur in Earth-like environments to be possible. If water can exist in such remote and hostile regions of space, the possibilities for life elsewhere are boundless. Furthermore, this discovery may prompt a re-evaluation of how we define habitable environments. While much of the focus in the search for extraterrestrial life has been on planets with liquid water on their surfaces, this finding shows that water in vapor form can also play a crucial role in the development of star systems and potentially life. The presence of water around quasars might be an early indicator that the building blocks for life are scattered throughout the universe, even in the most inhospitable and distant places. So why is this discovery significant? The discovery of this massive water reservoir opens up new frontiers in both astronomical research and the search for life. In the coming years, as our technology continues to improve, scientists will be able to study these distant regions in even greater detail. New telescopes and observatories such as the James Webb Space Telescope will allow astronomers to look even further into the past and study the conditions in the early universe with unprecedented clarity. In addition to studying water in distant galaxies, future research will also focus on understanding how such vast amounts of water can exist in these far-off regions. Is it a product of unique cosmic conditions? Or is water more common in the universe than we ever realized? How does water interact with other molecules in space? And what role does it play in the evolution of galaxies, stars, and planets? As our understanding of the universe deepens, the discovery of a massive water reservoir 12 billion light-years away reminds us of the vastness of the cosmos and the incredible mysteries that lie ahead. It shows us that even in the farthest reaches of space, we can find signs of the processes that shape galaxies and potentially foster the conditions for life. The quest for knowledge is far from over, and discoveries like this remind us that we are just beginning to scratch the surface of understanding the true nature of the universe. Quantum tunneling. Quantum tunneling is a fascinating and counterintuitive phenomenon in quantum mechanics, where particles can pass through potential barriers that they classically should not be able to cross. This phenomenon seems to defy common sense and the laws of classical physics, but it's a fundamental aspect of quantum theory that plays a crucial role in many natural processes and technological advancements. Quantum tunneling is not just a theoretical curiosity, it is a real, observable effect that has profound implications for fields ranging from nuclear fusion to semiconductors and even the workings of the universe itself. To understand quantum tunneling, it's important to first grasp a few key concepts of quantum mechanics. Unlike classical physics, which deals with objects moving in predictable ways based on forces like gravity, quantum mechanics describes the behavior of particles at the smallest scales, like electrons, photons, and other subatomic particles. In the quantum world, particles don't have precise positions and velocities like in classical mechanics. Instead, they are described by a wave function, a mathematical function that gives the probability of finding a particle in a particular location or state at a given time. One of the key principles of quantum mechanics is the wave-particle duality, which means that particles like electrons exhibit both particle-like and wave-like properties. This duality is crucial for understanding how quantum tunneling works. When a particle is not confined to a single location, but instead behaves like a wave, its probability distribution is spread out over space. In classical physics, if a particle doesn't have enough energy to overcome a potential barrier, such as a hill or wall, it simply cannot pass through. For example, if a ball doesn't have enough speed to roll over a hill, it will just stop at the bottom. However, in the quantum world, things are not so straightforward. A quantum particle can exhibit behaviors that defy classical expectations, thanks to the wave-like nature of particles. A potential barrier refers to a region where a particle would require more energy to overcome than it currently possesses. Classically, if a particle doesn't have enough energy to surmount the barrier, it would be reflected back. However, quantum mechanics allows for a different possibility. The particle can tunnel through the barrier, even if it doesn't have the energy to surpass it. So how quantum tunneling works? Quantum tunneling occurs when a particle encounters a potential barrier. The key to tunneling lies in the wave function. In regions where the particle's energy is less than the height of the barrier, the wave function does not abruptly drop to zero, as one might expect from classical physics. Instead, it gradually decays within the barrier. This means there is still a non-zero probability of finding the particle on the other side of the barrier, even though the classical rules would dictate that the particle should be unable to pass through. Think of it like this. If you roll a ball toward a hill, classically, if the ball's speed isn't high enough, it won't make it over the top. But in quantum mechanics, the ball's wave-like nature means that there's a small probability it might appear on the other side of the hill, even if it doesn't have enough energy to climb over it. The probability of tunneling depends on several factors, including the height and width of the potential barrier, as well as the particle's energy. If the barrier is narrow and the particle's energy is high relative to the barrier, tunneling is more likely. Conversely, if the barrier is very wide or the particle's energy is much lower, the probability of tunneling decreases. Quantum tunneling plays a vital role in several natural and technological processes like nuclear fusion in stars. In the cores of stars, hydrogen atoms fuse to form helium, releasing energy in the process. According to classical physics, the positively charged protons should repel each other due to the electromagnetic force, meaning They should never collide with enough energy to overcome the repulsion and undergo fusion. However, quantum tunneling allows the protons to tunnel through the repulsive barrier and come close enough for the strong nuclear force to take over and fuse them together. This process is crucial for the energy production of stars, including our Sun. Radioactive decay. In certain types of radioactive decay, such as alpha decay, an unstable nucleus can emit an alpha particle, 2 protons and 2 neutrons. The alpha particle is trapped within the nucleus by a potential barrier created by the nuclear forces and the Coulomb barrier due to the positive charge of the alpha particle. Classically, the alpha particle would not have enough energy to escape the nucleus. However, quantum tunneling allows the alpha particle to escape, leading to the decay of the parent nucleus. This is another example of quantum tunneling in action. Semiconductors and electronics. Quantum tunneling is also integral to modern technology, particularly in the field of semiconductors and electronics. In transistors, the building blocks of all modern electronic devices, electrons can tunnel through thin insulating barriers, allowing current to flow in ways that would be impossible in classical circuits. This effect is especially important as electronic components get smaller, with tunneling playing a significant role in the operation of devices like flash memory and quantum computers. Scanning tunneling microscope, STM. The scanning tunneling microscope, STM, is a device that uses quantum tunneling to image surfaces at the atomic level. The STM works by positioning a sharp metal tip very close to the surface of a material. When the tip is close enough, electrons can tunnel between the tip and the surface, creating a current that can be measured. This tunneling current is used to map the atomic structure of the material with remarkable precision, enabling scientists to study surfaces at the atomic scale. Quantum tunneling doesn't just affect small-scale phenomena, it may also play a role in the large-scale processes that shape the universe. For example, vacuum decay, a process in which the universe transitions from a metastable state to a lower energy state, involves quantum tunneling. In this scenario, a bubble of true vacuum could tunnel through the false vacuum, potentially altering the fundamental laws of physics. While this event is purely hypothetical, it underscores how tunneling could influence the very fabric of space and time. Another significant cosmological event involving tunneling is the Big Bang itself. Some models suggest that the early universe began as a quantum fluctuation, with the rapid expansion of space initiated by quantum tunneling from a high-energy state into the more stable state we observe today. Quantum tunneling is a testament to the strange, non-intuitive nature of the quantum world. It challenges our classical understanding of the universe, where the idea of a particle passing through an impenetrable barrier is impossible. Yet, in the quantum world, this is an everyday occurrence. The phenomenon forces us to rethink our fundamental assumptions about the nature of reality, energy, and matter. At the same time, quantum tunneling has opened the door to revolutionary technologies, from nuclear fusion to the development of more powerful and efficient electronic devices. Tunneling is an essential concept that underpins much of the progress in modern science and engineering. As our understanding of quantum mechanics continues to deepen, we can expect tunneling to play an even more significant role in future advancements, particularly in the realm of quantum computing, which promises to revolutionize information processing. The universe's network. It is often called as cosmic web, is the universe's grand architecture, a vast network of filaments composed of dark matter, galaxies, and intergalactic gas. Stretching across billions of light years, it forms the scaffolding of the cosmos, connecting clusters of galaxies in an intricate web-like structure. This colossal structure did not arise by chance, but through the relentless interplay of gravity and dark matter. In the earliest moments after the Big Bang, tiny quantum fluctuations in the primordial soup of the universe served as seeds for structure formation. Over billions of years, these fluctuations grew under the influence of gravity, pulling matter into dense filaments and nodes, while leaving behind vast empty voids. The result is a cosmic network of interconnected filaments stretching across the observable universe. At the intersections of these filaments lie galaxy clusters, the densest regions of the universe. These clusters, containing thousands of galaxies, are the hubs of the cosmic web. Between these clusters lie the filaments themselves, composed of dark matter and intergalactic gas, which form highways of matter and energy spanning cosmic distances. The voids, in contrast, are vast expanses of near total emptiness, where galaxies are few and far between. The cosmic web scale is almost incomprehensible. Each filament spans hundreds of millions of light years, and the entire web stretches across the observable universe. Yet, its intricate patterns resemble those of natural systems on vastly smaller scales, such as neural networks or the distribution of nutrients in biological systems. This resemblance hints at universal principles underlying structure formation, transcending the boundaries of scale and context. Studying the cosmic web has profound implications for our understanding of the universe. By mapping its structure, astronomers can infer the distribution of dark matter, the elusive substance that makes up about 27% of the universe's mass energy content. Dark matter does not emit or absorb light, but its gravitational influence shapes the cosmic web, making it a critical component of the universe's architecture. The cosmic web also holds clues to the universe's expansion. The web's growth and evolution are influenced by dark energy, the mysterious force driving the accelerated expansion of the universe. By studying the web's large-scale structure, scientists can gain insights into the properties of dark energy and its role in shaping cosmic history. Despite its grandeur, the cosmic web remains a dynamic system. Filaments grow as matter flows into them, and galaxy clusters merge and evolve over time. The web's evolution is a testament to the universe's ongoing transformation, driven by the interplay of gravity, dark matter, and dark energy. It is a reminder that even the most enduring structures in the universe are subject to change and renewal. The cosmic web is more than just a scientific construct. It is a symbol of the universe's interconnectedness. It reveals the profound unity of all matter, from the smallest particle to the largest galaxy cluster. It also highlights the duality of existence. The dense filaments and nodes are balanced by the vast voids, creating a tapestry of light and shadow, presence and absence. In contemplating the cosmic web, we are reminded of our place in the grand scheme of things. We inhabit a tiny corner of this immense network, bound to the rest of the universe by invisible threads of gravity and energy. The web's beauty lies not just in its scale, but in its ability to inspire wonder and curiosity, urging us to explore the cosmos and seek our place within it. Through advanced telescopes and simulations, humanity continues to unravel the secrets of the cosmic web. Each discovery brings us closer to understanding the universe's origins, its present state, and its ultimate fate. The web's intricate patterns, shaped by fundamental forces and cosmic time, stand as a testament to the profound interconnectedness of all things. It is a reminder that in the vastness of the cosmos, we are all part of a larger whole, connected by the invisible threads of existence. Blazars. Blazars are among the most energetic and fascinating objects in the universe. These are a specific type of active galactic nucleus, AGN, powered by supermassive black holes at the centers of galaxies. What makes blazars unique is their orientation. The relativistic jet emitted by the black hole is pointed almost directly toward Earth, making them extraordinarily bright and dynamic. The energy output of a blazar is staggering, often outshining the combined light of all the stars in its host galaxy. This immense luminosity originates from the accretion disk surrounding the black hole. As matter spirals into the black hole, it is compressed and heated to extreme temperatures, releasing vast amounts of energy across the electromagnetic spectrum. A fraction of this infalling matter is ejected along the black hole's rotational axis at near light speeds, forming a relativistic jet. The jet's composition is a mixture of high-energy particles and magnetic fields. As these particles spiral along the magnetic field lines, they emit synchrotron radiation, producing the blazer's characteristic brightness in radio, optical, and X-ray wavelengths. High-energy interactions within the jet also generate gamma rays, making blazers one of the most potent sources of gamma-ray emissions in the universe. Blazers are categorized into two main types: BL Lacertae objects, BL lax, and flat-spectrum radio quasars, FSRQs. The distinction lies in their optical spectra. FSRQs exhibit strong emission lines, while BL lax have weak or no emission lines. Despite these differences, both types share the defining feature of a jet oriented toward Earth, leading to their dramatic variability and high energy emissions. One of the most intriguing aspects of blazers is their variability. Blazers can change in brightness over timescales ranging from minutes to years. This variability is due to changes in the jet's structure, fluctuations in the accretion disk, and interactions with surrounding matter. These rapid changes make blazers valuable laboratories for studying relativistic jets and the physics of extreme environments. Blazers are also significant for their role as cosmic beacons. Their intense brightness allows astronomers to study the intergalactic medium and the distribution of matter in the universe. Gamma rays from blazers interact with background radiation, producing electron-positron pairs that leave detectable imprints on the gamma-ray spectrum. By analyzing these imprints, scientists can probe the properties of the universe on large scales. Moreover, blazers are crucial for understanding the processes occurring near supermassive black holes. They provide insights into the mechanisms of jet formation, the role of magnetic fields in shaping jets, and the interactions between jets and their surroundings. These studies have implications for our broader understanding of galaxy evolution and the interplay between black holes and their host galaxies. Blazers also serve as potential sources of high-energy cosmic rays and neutrinos. Recent observations have linked blazers to high-energy neutrino events detected on Earth, suggesting that these extreme objects may play a role in accelerating particles to energies far beyond what human-made accelerators can achieve. This connection between blazers and cosmic rays opens new avenues for multi-messenger astronomy, combining observations of light, neutrinos, and cosmic rays to study the universe. Despite their immense energy and significance, many mysteries about blazers remain. How are jets launched and collimated? What determines the variability timescales? How do interactions between jets and the interstellar medium influence their evolution? Answering these questions requires a combination of theoretical modeling, simulations, and observations across multiple wavelengths. Blazers, with their breathtaking power and complexity, epitomize the extremes of the universe. They remind us of the immense forces at play in the cosmos and the ingenuity of human efforts to comprehend them. As we continue to study these cosmic lighthouses, they illuminate not just the distant reaches of the universe, but also the fundamental processes that govern its workings. Cosmic collisions. Cosmic collisions are the universe's grand-scale catastrophes, each one marking a dramatic chapter in the ongoing saga of cosmic evolution. These events, ranging from the violent merging of galaxies to the catastrophic collisions of stars, showcase both the destructive and creative forces at work in the cosmos. They serve as reminders of the immense scale and complexity of the universe, where even the most catastrophic occurrences often lead to new forms of creation and evolution. Among the most awe-inspiring of these collisions are galaxy mergers. When two galaxies collide, the process can take millions to billions of years. Despite the vast distances between the stars within each galaxy, these gravitationally bound giants can cause profound distortions in each other's shapes. As the galaxies interact, Tidal forces create spectacular structures known as tidal tails, long streams of stars and gas. These interactions also often trigger intense bursts of star formation, with the gas clouds within the galaxies compressed and igniting new stars in a chaotic process. Eventually, after many cosmic years of merging and reshaping, the two galaxies settle into a new, larger, and often more irregular galaxy. This process of galactic evolution is not only violent but also creative, giving rise to entirely new star systems and structures in the process. On smaller scales, the collision of stars can be rarer but far more dramatic. When two stars collide or merge, the results can be extraordinarily energetic. These stellar collisions can lead to the formation of exotic objects like blue stragglers, stars that appear younger and more massive than other stars in their vicinity. More often, however, the collision of stars leads to catastrophic events such as supernova explosions. These violent stellar deaths send shockwaves through space and disperse vast amounts of energy and heavier elements into the surrounding interstellar medium. These explosions are essential for the creation of the elements that make up planets and life itself. In addition, the planetary systems around the colliding stars are often destroyed or ejected, leaving behind a legacy of chaos and transformation. Even on Earth, cosmic collisions have shaped our destiny. The asteroid impact that led to the extinction of the dinosaurs is perhaps the most famous example of how a collision from space can alter the course of life on a planet. Such impacts are reminders of the fragility of life in the face of the immense forces of the cosmos. But this is not the only time Earth has faced a cosmic catastrophe. In fact, the planet has been subjected to numerous asteroid and comet impacts over its history, each of which has played a part in shaping Earth's geological and biological development. These collisions, while catastrophic, have also been responsible for creating conditions that eventually allowed life to flourish on our planet. Looking into the distant future, Earth may again be affected by cosmic collisions. One of the most significant events on the horizon is the anticipated collision between our Milky Way galaxy and the Andromeda Galaxy. This event, expected to occur in about 4 billion years, will reshape our cosmic neighborhood. While the stars within each galaxy will pass by each other without direct collision due to the vast distances between them, the gravitational forces between the two galaxies will dramatically alter their shapes. New structures may form, and the solar system itself could be disturbed, though humanity may no longer exist to witness this grand event. The Milky Way and Andromeda will likely merge into a new, massive elliptical galaxy, a process that will be both destructive and transformative. Cosmic collisions, while often destructive, are also fundamental agents of creation. They play a crucial role in galaxy evolution, star formation, and the creation of the elements essential for life. In their chaos and violence, these collisions reflect the universe's dual nature, a realm of constant destruction and rebirth. They highlight the ongoing process of cosmic renewal, where the destruction of one structure paves the way for the birth of something new. These events underscore the cyclical nature of the universe, where nothing truly ends, but instead transforms into something else. Through cosmic collisions, the universe continues its eternal dance of creation, evolution, and renewal. The study of cosmic collisions not only deepens our understanding of the universe, but also brings a sense of awe and wonder at the scale and complexity of the cosmos. As we explore the far reaches of space, we witness the aftermath of these colossal events, revealing the hidden forces that shape the very fabric of the universe. Whether through the merging of galaxies or the explosion of stars, cosmic collisions remind us that even in the darkest and most violent moments of the cosmos, there is always the potential for new beginnings and the ongoing creation of new worlds and life. The universe, in its vastness, unveils phenomena so extraordinary that they defy our comprehension, reminding us of the boundless mysteries that await discovery. From immense water reservoirs orbiting distant quasars to the intricate dance of galaxies and stars, the cosmos is a never-ending testament to the creativity and chaos woven into its fabric. These wonders challenge our understanding of life, existence, and our place within this grand expanse. In our pursuit of knowledge, we are humbled by the infinite complexities that persist beyond the reaches of our imagination. Hope you like this video. Please let us know which of these phenomena interest you the most. Thanks for watching.